Hi, welcome to Dissolved Chemistry. Let us continue our discussion on this thermodynamics. Okay, so we initiated our discussion on this second law of thermodynamics. What are the requirements for that? Now we will continue with the same. So lastly we concluded in the previous video that the total entropy change of the universe, if it is positive, then the process will be spontaneous. Okay, now we know that the total change in the entropy is equal to sum of the change in entropy of the system and change in entropy of the surrounding. Okay, now we know that change in entropy of the system somehow we can determine, but how much change in entropy of the surrounding occurs, its determination is difficult. And another thing is that in most of the cases we are going to bring the reactions or chemical processes are brought in closed vessel or in open vessel, which is having communication with the surrounding. So therefore, whatever the change in entropy of the surrounding is there, it is very difficult to determine. If the system is isolated, then we can determine only change in the entropy we are in need to check is that is of the system. So therefore, we can notice that if it is positive, then we can say that the process is spontaneous. If it is negative, we can say non-spontaneous. But when the reaction or the chemical process is brought in a open vessel, then it becomes very difficult to determine the change in entropy of the surrounding, or we can say it is not at all possible to determine. Now in such case, how to tell the spontaneity of the process? So to tell that spontaneity of such processes, a new term or the function was being introduced, and that function is your Gibbs free energy change. Okay, so that we are going to represent as delta G, because it's not possible to determine absolute value, so therefore we represent this as delta G, change in free energy of the system. Okay, and how we are going to define this? The Gibbs free energy of the system is defined as Gibbs free energy of the system is defined as the maximum energy available with the system during the process that it can utilize to convert into useful work. Okay, so the Gibbs free energy of the system is defined as the maximum energy available with the system during the process that it can utilize to convert it into useful work. Okay, and mathematically we are going to give it as delta G is equal to delta H minus T delta S. Okay, as we have said, it includes both the terms here. Delta S, it is a change in entropy of the system, and it is change in enthalpy of the system. Means both energy term and entropy terms are being utilized to define Gibbs free energy, and we can tell the spontaneity of the process. Okay, so let us go in detail with this. Consider a system. Okay, now what happens? the Q amount of the heat is given out by the system. Okay, so Q amount of heat is coming out of the system. Okay, then what happens? The same amount is being received by the surrounding. So therefore we will represent as plus Q surrounding. Okay, so now how we are going to relate these two? See here. So when the Q minus of the system means amount of energy given out by the system is equal to amount of energy absorbed, that is plus Q of the surrounding. Okay, now Q plus of the surrounding, we know that minus Q of the system, or we can call it as what? Change in enthalpy of the system. So therefore Q amount of heat absorbed by the surrounding will be equal to Q amount of the heat given out by the system, or change in enthalpy of the system, we can say. Okay. We know that the total entropy change of the universe is equal to change in entropy of the system, okay, plus change in entropy of the surrounding. And already we brought the relation. Okay, so let us know that. So therefore delta S of surrounding is equal to, you make note of this side by side, surrounding is equal to what? Minus delta H, or we can write like this, Q of the surrounding divided by T. So therefore already we know that Q of the surrounding is equal to minus delta H. So therefore minus delta H of the system, okay, divided by T. So that let us substitute in this equation. So therefore it turns out to be what? Delta S of the system, okay, plus instead of this delta S of the surrounding, what we can do is we will write like this, minus delta H of the system divided by T we are going to get. So now delta ST is equal to this one. Now let us simplify this. So what we can do is, so if you take T onto this side, then what you will be having? T delta ST is equal to T delta S of the system, S of the system minus delta H system. Okay, change the sign and you will be getting that one. So therefore minus T delta ST is equal to what you will be getting? Delta H minus T delta S. Okay, after changing sign on both sides, you take minus sign, if it will be minus and this will be plus. So therefore what happens? Minus T delta ST means product of temperature and total entropy of the universe is equal to delta H minus T delta S. Already we told you, so that delta G is equal to delta H minus T delta S. So therefore directly we will write, so delta G is nothing but, okay, it is the product of temperature, change in entropy of the universe. Okay, so now we are going to relate this with what? Already we know that one, or we can write like this, T delta ST is equal to minus delta G. Okay, so now we can see that one at what conditions of this change in free energy and change in total entropy of the universe are going to relate with the spontaneity of the process. Okay, so let us see that one. Okay, condition you take, okay, then you write change in entropy, change in Gibbs free energy. So these are how they are being related with each other, you know that. Okay, so now suppose if the process is spontaneous, then your delta ST will be what? Always positive. Then your delta G should be what? If it is positive, means this should be what? Negative. Right? Similarly, for non-spontaneous process, if it is negative, then what happens? It will be positive. Okay? The value of delta G will be positive. So if the system is at equilibrium, then both will be 0. Okay, you may please make note of these conditions because these are very important. Okay, so they will ask frequently on this. Right, now we will talk about what is the physical significance of this Gibbs free energy change. Okay, and spontaneity of the process. From this, what is clear? Any process to be spontaneous, the Gibbs free energy change for a given reaction should be always negative. Okay, so now let us look into its physical significance. Already we have said that absolute value we cannot determine for Gibbs free energy. Okay, it will be always change in Gibbs free energy. Well, so from the first law of thermodynamics, we know that the change in internal energy is equal to Q minus W, where W is what? Work done. Okay, and Q is amount of heat energy absorbed. Heat absorbed. Okay. Now this work will be going to include, we know that there are two types of works are there. One we call it as what? PV work, or we call it as what? Expansion work. Expansion work, we are going to represent this as pressure volume. And please make note of this regarding this expansion work. In very greater detail we have discussed in one of the video of thermodynamics. And then another one we call it as what? Non-expansion work. And it is also referred as what? Useful work. Useful work. Okay, or non-expansion work. Right? So therefore, this work we will include both expansion work as well as non-expansion work done by the system, because non-expansion work is not included in the first law of thermodynamics. You should make sure of that. So only we are talking about what we call a pressure volume change or expansion work only it considers. This non-expansion work, it is not included. So therefore we will see that one. So therefore delta U is equal to Q minus, okay, expansion work plus non-expansion work. Okay, we will include like this. Now let us multiply this minus sign into that. So then you will be having delta U is equal to Q minus, and we will take expansion work means what? P delta V, we know that one, and minus W non-expansion we can call. Okay, expansion work that we have defined as change, that is product of pressure into change in volume. Okay, Q minus, you take all these terms onto this side. So therefore Q is equal to what you will be having? Delta U plus P delta V plus W non-X S plus non-expansion work, or you can call it as a useful work. So now we know that this Q, okay, so is nothing but what? T into delta S. Okay, I will write it here. We know that change in entropy is equal to Q by T. So therefore that we have make utilization here. So that is T delta S is equal to delta U plus P delta V plus W non-expansion work. And what is this term is called? We can represent as what? What is that? Delta H. Delta U plus P delta V is nothing but change in enthalpy of the system plus non-expansion work. So now you take on this delta H on this side. Okay, so then you will be getting ending with what? Here we will write, fine, okay. So therefore, minus delta H plus T delta S is equal to W non-expansion. So now what we will do, so we'll change the sign, that is delta H minus T delta S is equal to minus W non-expansion, okay. And we know that delta H minus T delta S is nothing but whatever delta G. Delta G is equal to non-expansion or useful work. Okay, so this is how we are going to check its physical significance. If you want to draw an what we call useful work from the system, then what we need, the change in Gibbs free energy during that process should be what? Useful work, we call this, right? So the change in free energy should be negative. If it is more and more negative, then the process will be more and more spontaneous, and you can draw the energy, okay, into useful work. Okay, I hope you have understood up to this, right? So what is its importance is that whenever the process occurs, okay, it is said to be spontaneous when its free energy change is more negative. Okay, is it clear? Already we have mentioned the condition, change in free energy. If it is negative, then it is spontaneous. If it is positive, it is non-spontaneous. And if it is equal to 0, then we call it as what? At equilibrium. So next we will talk about standard Gibbs free energy change. It is represented as delta G naught. Okay. Now for any process, if you determine the change in free energy at a 298 Kelvin temperature and 1 bar pressure, so then whatever the Gibbs free energy change is there during that process, that is said to be standard Gibbs free energy change of a reaction or process. Okay, so that is the free energy change during a process which is carried out at 298 Kelvin temperature and 1 bar pressure. Okay, then it is called standard Gibbs free energy. Change. Okay, and we are going to give mathematically as delta G naught is equal to delta H naught plus T delta S naught. Okay, for a given reaction. Okay, so we'll see that one. For a reaction, okay, so at any moment of the, or at any instant of a reaction, the Gibbs free energy change is given as delta G is equal to delta G naught plus RT ln Q. Okay, where Q is reaction coefficient. Reaction coefficient, or we can call it as at any moment of the reaction prior to attaining the equilibrium, we call. Process is at equilibrium, then we give Gibbs free energy change will be is equal to delta G naught plus RT ln Kc. Okay, and we know that at equilibrium delta G is equal to 0. Already we know the condition. So therefore if you substitute, then what happens? Delta G naught is equal to minus RT ln K. Okay, so then ln K is equal to what it turns out to be. Suppose ln K is equal to, you will be getting what? Delta G naught by RT, minus sign it will be there, and K is equal to e to the power minus delta G naught, okay, by RT. So this is how we are going to give the equilibrium constant, Gibbs free and standard Gibbs free energy change relation with the equilibrium constant. This is how we are going to bring. Or we can write like this: delta G naught at equilibrium is equal to minus 2.303 RT log to the base 10, okay, K we can call. Okay, so this is also another relationship we are going to use. So this is how various different forms of Gibbs free energy and under different conditions of the reactions we are going to represent. Okay, so, and in the next video we are going to discuss regarding how we relate this Gibbs free energy change with the spontaneity of the process. Okay, for more details about different aspects of thermodynamics, please watch our videos which are available in YouTube. Okay, and please don't forget to subscribe our channel. Thank you.